All right, everybody. How we doing? Coming at you with lecture video 2 for chapter number 14 here. Getting right into talking about pH. Okay, now, definition of pH right out of the gate is a measurement of the amount of H plus ions an acid or technically a base has in solution. So it's just a pure measurement, guys. I know obviously pH is something that you guys have all dealt with in the past. Whenever you've talked about sort of anything acid and base related. Whether we're talking about it maybe in your most recent biology class last year or the year before, or even if you learn about anything acid and base related, maybe in middle school science, right? pH is probably going to be the one thing that was covered in those classes. But really, guys, at the end of the day, it's just a measurement of the amount of H plus ions that an acid, again, or a base has in solution. Here's the equation, right? In this equation, thankfully, for you guys is on your end is present inside your reference tables on table T towards the very, very bottom there. But the pH equation is a pretty basic one. It seems like it's kind of a, it's going to kind of be a lot. It's including a logarithm here, right? The log function that's going to be at your calculators there. But really, it's not all that crazy. There's really only two places you can actually input into your calculator when it comes to using this equation. And we'll learn more about it when I see you guys next in class. But one thing I do want to hit on here, guys, is the fact that in this equation here, you've got two brackets here around this H plus ion. This is something that's kind of be a recall from when we did our rate of reaction lab, and you guys had those data tables where, one of the columns actually had the letter A in brackets, and I said in class that day, I said, hey guys, something we'll learn very soon is that whenever you have a set of brackets around something, it's just a very, very shorthand way of saying the concentration of whatever's inside your brackets here, right? So if we've got an H plus here in brackets, all we're saying is we're talking about the concentration of H plus ions, right? That's, of course, measured in molarity, right? Capital M, which is that molarity we dealt with back in chapter 13. Now, one thing to be absolutely sure, though, guys, is the presence of this log function in the equation. And if you know anything about logs, it's that the log represents a tenfold change in general, right? So whenever you deal with a logarithm or a log function on your calculator or in graphing or whatever, right? Logs have a tenfold change. So they ramp up pretty quickly. So whenever you've got a change in pH of only 1, let's say from a pH that's been measured from, let's say, a pH of 5, and it changes and decreases from a pH of 5 down to a pH of 4, right? It might not seem like a crazy jump, pH of 5 down to pH of 4, but whenever there is a change in, of 1 pH unit, it's going to indicate a tenfold change in the concentration of those H plus ions. So like, for example, if we're decreasing pH by 1 from 5 down to 4, that's going to actually represent a tenfold or a 10x change in the concentration, making it more acidic. Whereas on the flip side, let's say we go from 4 up to 5, right? That's going to be only a change of pH in only 1 unit, right? From 4 up to 5, right? Change in 1. But that change in the concentration then of those H plus ions is going to be 10 times, right? In this case, a 10 times decrease, making it less acidic in this case here. And I'll explain and flesh out that more in class. Now the pH scale, right? That's going to kind of be the thing that you guys deal with the most here or have dealt with in the past the most here. The pH scale, of course, in the dead center is 7. All the way over to the right is going to be a 14. And all the way to the left is going to be a 0. Now the range from 7 all the way to 0 is a representation of more acidic. I'll do my best writing this with a mouse here, so mind my handwriting here. The range from 7 all the way down to 0 is going to be more acidic, and then the range from above 7 all the way up to 14, of course, is going to be more basic. All right, so from 7 all the way down to 0 is going to be more acidic, and then from above 7 up until 14 is more basic. But again, we have to be very sure, guys, that 7 means exactly neutral. I'll probably butcher this here, but this is neutral, okay? Neutral, neutral, okay? 7 exactly is neutral, right? And one thing to be absolutely sure is that even if you've got a number like, 7.01, okay, a pH that's equal to 7.01. If it's not exactly 7, it's not neutral, plain and simple, right? This number, 7.01, looks pretty darn close to 7, right? It's only about, tenths of the way off from being a 1 with this 0.1 present here. But I have to be, honest, guys, it's not 0, or rather, it's not 7, okay? If it's not 7, it's not neutral, plain and simple. It has to be exactly 7 in order for it to be neutral, okay? If it's not exactly 7, even a little bit up above it or a little bit below it, it's going to be acidic or basic technically, okay? Now, neutralization reactions, right? We obviously spent a little bit of time last class talking about dissociation reactions, guys, but these neutralization reactions are going to be a little bit different here, okay? Different type of reaction, different type of reactants forming into a different type of products here. So short and simple, a neutralization reaction is a reaction in which an acid and a base react to produce two things, salt and water. Now, the nice thing about it, guys, is that they are pretty consistent with this. And right here, what I've got here for you guys is what's known as the general equation for a neutralization reaction. It's the general equation because it's always going to be the same thing, creating and being formed from it, right? So you're always starting with some acid and some base reacting together, and you're always forming two things, salt and water. So that's the nice thing about this, right? Whenever it comes to predicting the products, you can always be absolutely sure that one of those two products is going to be H2O, which is very, very convenient for us all, which means the only real product you have to think about is going to be the salt, okay? Now, one thing, and I'll clarify this as well in class, is that obviously whenever you guys think of the word salt, 9 times out of 10, the first compound that comes to mind for you all is NaCl, right? Table salt, right? Sodium chloride. And that's, that can be true, right? Table salt, NaCl can be formed in these neutralization reactions, but it's not always going to be the case. Whenever you talk about salt in the realm of chemistry, guys, any kind of salt is going to just be a general ionic compound. So ionic compounds could really be anything. It could be KCl. It could be, it could be a number of different, different ionic compounds. All the different ionic compounds that we've learned about back in chapter 5, back in November, December, guys, always going to be different types of salts, right? It's just a basic way of calling something an ionic compound if it's a salt. Now, in order to specifically achieve this neutralization reaction, guys, you have to make sure that your acid and base are combined in equal amounts, all right? If you have a ton of acid, only a little bit of base, just mixing those together is not going to achieve this neutralization reaction, right? Because all this extra acid you had here is only going to, it's going to still create a very, very acidic solution. So if you have a ton of acid and only a little bit of base, all of this majority acid is going to kind of, take over that additional base and still make the solution, be more acidic than anything else. So you have to have equal parts of acid and base in order for this to work. Now, one of the sort of physical components of these neutralization reactions is that they give off a lot of heat. Generally speaking, though, they only give off a lot of heat if you've got really high concentration, right? High molarity acids and high molarity bases. So, for example, HCl, of course, is an acid. NaOH, of course, is a base. And we can kind of see those guys, right? Because, again, HCl has the H in front that we can kind of notify as an acid. And then NaOH, of course, has the OH here, our hydroxide that we always look for to try and help determine if something is a base, right? Now, how does this break down, right? How are we able to just instantaneously say that, hey, combining HCl and NaOH produces NaCl and H2O? How do we get to that point? Okay, well, it's pretty simple. Okay, whenever you look at these reactions here, the N or the H rather, the H from HCl from your acid and the OH from your base, in this case, our NaOH. These guys are always going to come together to form water every single time. So this H and this OH here will always come together to form, which is technically HOH, right? But again, when we mix this thing up here, HOH really does just, in turn become H2O. Now, what's left over then, of course, is your Na and your Cl. So these guys have to then combine together on their own to then form NaCl. Okay, so that's kind of how these reactions work. Again, we always know that water is going to be one of our products, right? Again, the only thing we have to really physically do in terms of any legwork really is just coming up with the remaining ions to create your salt here, okay? So H2O is always going to be one of the reactants, right? So you get the H plus ion and the OH minus ion to form to create H2O, and then the remaining ions left over have to form the salt. Now the problem, that you guys end up running into here, unfortunately, is the fact that whenever you've got these ions left over, the Cl minus ion and the Na plus ion, right, we have to be absolutely certain to remember the crisscross method. I'm going to do a very basic example with these two ions for us all here, right? The crisscross method takes two different ions that you want to combine together to form a compound and allows you to get the subscripts of these ions down pretty much instantaneously, remembering that we take the number and just the number, not the charge. Maybe we can make a better circle here. Okay, just the number and not the charge here, and cross these down to become the new subscripts for our substances here, right? Of course, these are both ones here telling us exactly how many NAs we have and how many CLs we have. So this really just does become NaCl without any subscripts present here, right? But again, if there technically was, let's say for example, if there technically was a 2 here, that would just simply say that, hey, I've got 2 NAs, so I'd have to have Na2Cl as our, one of our reactants here, right? So again, we have to be darn sure that all of our crisscross method stuff is down from a while ago, and we have to, bring it back to help us out in this particular chapter here, okay? Now, what are the steps to write a neutralization reaction? We kind of just went over them here, but let's just break them down into some more general steps here. Write the general formula. But the general formula here, guys, is going to be this thing right here. Acid plus base equals salt plus water. That's the general form. I would recommend, at least to start out here, write that general form, and you can kind of plug into that general formula to kind of help you along the way, so you kind of know for sure that, hey, this is where the acid and the base is supposed to go, and this is where the salt and the water is supposed to go. It's going to kind of help you out, flesh it out in the early stages here. And then, once you have that general formula, substitute the acid and the base for the actual formulas, whether it's HCl or HNO3, whatever the acid may be, and whatever the base might be, NaOH, CaOH2, whatever the base may be. Plug that formula into acid and base. And then, of course, always make sure you're identifying your H plus ion from your acid and your OH minus ion from your base. That's going to help you form your water always, right? Because again, general formula always says we are creating water. We're always creating H2O every single time, okay? Then, from there on out, you can just kind of use the remaining ions to form your salts. Balance the equation as necessary, and there you go. Oops. All right, so continuing on now with another type of reaction here. Again, neutralization reactions are one reaction, whereas these other ones, these are called acid-metal reactions. A little bit of a different story here, okay? They are a type of reaction where acids are going to react directly with a metal, a solid metal, to produce hydrogen gas this time around, okay? So a little bit similar in regards to a neutralization reaction, where neutralization reactions are always going to be creating water here, right? We just showed that, right? Always going to be creating H2O in a neutralization reaction, but in an acid-metal reaction, you're always going to be producing H2 gas, hydrogen gas, right? So for example, this right here, guys, magnesium, Mg, reacting with HCl, hydrochloric acid, is going to form always, number one, H2 gas, hydrogen gas, but it's going to also produce a byproduct, in this case being MgCl2. This reaction right here of magnesium mixing with HCl is the exact same reaction that you guys actually did in a lab not too long ago, that moles of hydrogen gas lab, where you got to see the little strip of magnesium metal mixed with the HCl to produce all those bubbles and whatnot, right? And then obviously capture the hydrogen gas you were producing, capturing it in that gas tube and then using that to help measure your pressure, right? So here's an example problem. We'll talk about it more in class, but jot this down. And then lastly, talking about acid-base indicators. I'm going to kind of save a lot of this. Obviously, take the second to jot all this down. I'm going to save a lot more of this talk about acid-base indicators for when we're actually in class and we can do some examples and whatnot surrounding it. So again, jot all this information down, and I will see you guys in class to talk more about acid-base indicators.